Chapter 2, Atoms, Molecules, and Ions. Our outline is Early Experiments, Introduction to Atomic Structure, Periodic Table, Molecules and Ions, Nomenclature. Early Experiments. In chemistry, we use the terms reactants and products. Reactants are what are going to react. They're written on the left side, and they form products. We indicate forms with the arrow. We can also say that's the yield symbol. Reactants yield products. In the late 1700s, a scientist named Lavoisier weighed reactants and products of reactions and found a constant observation. The mass of all the products equaled the mass of all the reactants. This was repeated over and over, and it was consistently observed. And so this observation that mass equal products became a law, and it's called the law of conservation of mass. Mass is conserved in a chemical reaction. In the early 1800s, another scientist, an English scientist named Dalton, worked with predicting molecular formulas. This and other work led to various hypotheses that help to determine the correct molecular formulas of compounds. For example, water was known to contain hydrogen and oxygen. What is the ratio of the two? Well, it was determined to be H2O, 2 hydrogens for every 1 oxygen, not, for example, HO, which would imply 1 hydrogen for every oxygen. In this time period, more elements were being discovered. In the late 1800s to early 1900s, the discovery of the composition of the atom and how atoms differ was discovered. A scientist named J.J. Thomson set up this apparatus that we're viewing here, where he had 2 pieces of metal separated. He had one on the left side, one on the right side, and he enclosed them in a glass covering, and he applied a high voltage difference, a high electric field difference, where the left one was the negative plate and the right one was the positive plate. And when he applied that high voltage, he found that particles were given off that went from the negative plate to the positive plate. That would imply that they had a negative charge since they were attracted to the positive plate. When he applied an electric field top and bottom, he also found that the particles given off were attracted to the positive plate. So it was determined that this was a stream of negative particles, which we now call electrons and symbolize E-. He found that various types of metals all produced electrons. Thus, all atoms must contain electrons. He found the charge to mass ratio to be negative 1.76 times 10 to the 8th coulombs per gram, where coulomb is a unit of charge, the metric unit of charge. Another scientist named Millikan found in 1909 the charge of the electron to be QE, where Q is a common symbol to indicate we're talking about charge. QE is equal to negative 1.602 times 10 to the negative 19 coulombs. So that indicates it's got that negative charge that J.J. Thomson had determined, and that's its value in Coulomb. In the relative unit that you might be used to from a previous chemistry class is the charge of the electron is -1. Well, that comes about if we take the -1.602 times 10 to the minus 19 Coulomb and we divide by 1.602 times 10 to the -19 Coulomb. So we're getting rid of the unit and it becomes just -1. That's our relative unit that we commonly think of as the charge of the electron. The mass of the electron was found then to be m sub e, mass of the electron, 9.109 times 10 to the minus 28 grams, so very, very tiny. Since atoms are neutral, atoms must contain something positive. So an atom, by definition, is neutral. Well, if it contains something negative, it's got to contain something positive to balance it. Thomson assumed a diffuse cloud of positive charge with electrons embedded in it and called it the plum pudding model. Okay, so Thomson was English, and the English have a kind of cake type dessert referred to as plum pudding. And so it's a cake with pieces of fruit in it, chunks of fruit, plums, I suppose, within it. And his model here was the cake part was the diffuse positive charge, so spread throughout the whole atom, this positive charge. And the pieces of plum were like the electrons, so they were here and there throughout the atom. In the late 1800s, a scientist named Becquerel accidentally found that a mineral containing uranium, so just a natural mineral that contained uranium, produced a particle that caused photographic plate that was located somewhere near this mineral to be exposed. So what he found was the uranium was giving off a particle, emitting a particle just on its own, spontaneously, and he called that process radioactivity. The emission particles were found to be helium-4 nuclei. So they are the nucleus of the helium atom, and they were named alpha particles. It was determined that the mass of the alpha particle is 7,300 times the mass of the electron, so very, very much bigger. And it had a charge of +2, so twice the charge and also the other sign. In the early 1900s, another scientist named Rutherford studied Thomson's plum pudding model. What he did was he directed alpha particles, so look at the diagram, alpha particles coming from the uranium source, they were located on the left are located on the left in our diagram. So he directed them to a sheet of metal foil, that's the gold sheet shown in the diagram. So the atoms within the metal were being bombarded by these alpha particles. And he had then a photographic plate just about surrounding this metal foil. And what would happen is the alpha particles would interact with the metal foil, and then they would go to the photographic plate, and that would indicate what was going on in that interaction. If Thomson were correct with his plum pudding model, then the massive alpha particles should go straight through the thin metal foil. Because remember that they are much, much bigger than the electrons, and their charge is 2+, but the charge of the atoms is diffuse throughout the atom, so there shouldn't be much interaction. The results are what are on the right here. Most alpha particles went straight through, but a few were deflected at big angles. So let's go to the diagram on the left first. That's the Thomson plum pudding model. Those big alpha particles would hardly be affected by the diffuse positive charge, so they would just primarily go straight through. Maybe they'd be a little bit attracted to the electrons. They have twice the charge, but of course opposite sign. But they would mostly go straight through. Well, most of them did go straight through, but some of them were deflected at quite the angles, as the actual results diagram shows us. He made a statement, something like, it was as if he shot a bullet at a piece of paper and it ricocheted back at him. So what that indicated to him was the atom must have a very highly positive center to interact so strongly with those alpha particles, causing them to be greatly deflected. That gave rise to our current model of the atom called the nuclear atom. The atom has a dense center of positive charge, which we call the nucleus, and the electrons are moving around the nucleus in the outer region, which we call the electron cloud. They are at a large distance from the nuclear center. So the size of the atom is very large in comparison to the size of the nucleus. Within the nucleus are the positively charged particles, which we call protons, which we can abbreviate P+. The nucleus is so tiny that if the nucleus were the size of a green pea, the atom, the full atom, would be the size of a baseball stadium. So with that in mind, we move to our next section called Introduction to Atomic Structure. All atoms are composed of protons, electrons, and neutrons, except for one atom, and that's the most common isotope of hydrogen we refer to as H1. We will come back to isotopes shortly. So, some information about the proton, the electron, and the neutron. For the proton, its mass in kilograms is 1.673 times 10 to the negative 27. Its mass in atomic mass unit, the unit U, where 1 U is 1.661 times 10 to the minus 27 kilograms, is 1.007 U's. So the atomic mass unit is a very, very tiny, the microscopic unit of mass. The charge of the proton is, in units of Coulomb, 1.602 times 10 to the minus 19. So it is the charge of the electron, but the opposite sign. In the relative unit, it's +1. So the electron, its mass in kilograms is the 9.109 times 10 to the minus 31. Mass in the atomic mass unit, 0.0005486, which is about 1/2000th times the mass of the proton. The charge of the electron we saw before, negative 1.602 times 10 to the minus 19 coulombs, or -1. The neutron, its mass is 1.675 times 10 to the minus 27 kilograms. In the atomic mass unit, it is 1.009 U, so just about the mass of the proton, a little greater. Its charge is 0. It's neutral. It's chargeless. The neutron and the electron, those are both located in the nucleus. The electron is in the electron cloud about the nucleus. The number of protons in the atom determines what kind of an element we're talking about. For example, hydrogen always has one proton. Or we could say if we have an ion or an atom of hydrogen, we have, if we have an atom or an ion that has one proton, we're referring to hydrogen. Hydrogen and one proton are, you might say, interchangeable. Helium has two protons, or we could say an atom or ion with two protons is helium. The number of protons in the atom is on the periodic table, and it is usually written above the symbol for that element. It's the whole number on the periodic table. The number of electrons determines the chemical properties. For example, hydrogen with no charge, hydrogen with a -1 charge, and hydrogen with a plus charge have different chemistry. Hydrogen with a minus charge has one extra electron. Hydrogen with a plus charge has lost its electron, because realize that if we're talking hydrogen, we always have one proton, so the number of protons does not change. All atoms of an element, like carbon, have the same number of protons, but not necessarily the same number of neutrons. Atoms or ions with the same number of protons but different numbers of neutrons are called isotopes. How we symbolize an isotope, we can do one of two ways. One way is to write the chemical symbol, and then as a superscript on the right, the charge. As a subscript on the left, the number of protons, which is what we also call the atomic number. So atomic number equals the number of protons. It, by the way, can be symbolized Z, and that's the quantity that we find on the periodic table. And then we have, as a superscript on the left, the mass number, where the mass number is the number of protons plus the number of neutrons. It can be symbolized with the symbol A. It is not on the periodic table. The charge is the number of protons minus the number of electrons. That's also not on the periodic table. The other way to symbolize an isotope is to write the chemical symbol dash the mass number. Alrighty, so here are some examples for you to work on, and remember that example answers, if they're not given within the handout as we go through them, they're at the end in the answer section. So our first problem in that table, the one on the upper left, is we have an atom where in the nucleus we have 6 protons and 6 neutrons, and in the electron cloud we have 6 electrons. So if we look to the periodic table, 6 protons means we're talking about carbon, so we would draw a big C. The number of protons equals the number of electrons, so the charge is 0. So we could write that as a superscript on the right, a 0, or we could leave it off. And then as a subscript on the left, we would put 6 for the atomic number, the number of protons. And then the superscript on the left, the mass number, we would write 12 because of 6 protons plus 6 neutrons. We could also symbolize it C-12. So do that for the other examples given to you. And here is another example. You're to fill in the table. So we're given the symbolism for an isotope, and for here, helium, for example, and we determine how many protons, neutrons, electrons, and so on it has. So we see the subscript is 2, so it has 2 protons, plus it's helium, so it has to have 2 protons. The number of neutrons is going to be 3 minus 2, or 1. The number of electrons, well, it's got no charge, so the number of electrons must equal the number of protons, so we would put a 2 there. The atomic number is the number of protons, so that's 2. The mass number is 3. So do that for these other ones and be sure to check your answers. Our next section is the periodic table. This representation with the green, purple, and blue is showing the metals, the nonmetals, the metalloids. So we see that the metals, those ones in that kind of gray-green color, those are the bulk of what we see on the periodic table. So those are on the left side and the lower side, except for hydrogen, that is a nonmetal. And then as we move to the right, we see the purple elements. Those are metalloids. So those have properties of the metals. They have properties of the nonmetals. They can also be called semi-metals. And then the elements on the most right side, those are nonmetals. Metals, you probably know those are good conductors of electricity, also good conductors of heat. When they become charged, mind you, they don't have to be charged. We can have a piece of aluminum foil that is composed of aluminum atoms without a charge, but when they become charged, they usually do so by losing electrons, and they become positively charged. A positively charged species we call a cation. They are typically solids at room temperature, but we do have exceptions. Mercury, which is number 80 on the periodic table, it is a liquid at room temperature. The other ones I give, gallium, cesium, francium, those are almost liquids at room temperature. In fact, gallium, if you were to put a piece of gallium metal in your hand, it would melt just due to your body temperature. Metals are malleable. They can be hammered into shape. They are ductile. They can be pulled into wire. Think of copper wire. Nonmetals, when they become ions, they do so by typically gaining electrons. A negatively charged ion we call an anion. Nonmetals are insulators. They don't conduct well. And they are typically gases and solids at room temperature, except for bromine, number 35, that's a liquid at room temperature. Notice on the periodic table we have the lower 2 rows, the lanthanides and the actinides. Those are metals. Within there we have uranium. These next representations of the periodic table, the one on the left, we see that it's distinguishing main group elements, those are those shown in yellow, from transition elements. Main group elements, they can also be called representative elements. They show a lot of trends. We will talk about trends as we move through the course. And when we are most likely talking about the main group, the representative elements. The transition elements don't show the trends quite as well. We study those primarily in Chem 2. In fact, we have a whole chapter on transition elements. By the way, the lanthanides and actinides, those are shown only in this upper periodic table. Those are also transition elements. Given that they are metals, we can call them transition metals. This periodic table on the right side, that is showing charges that when the substances become charged, they typically take on. Very handy because then you can If you need to know the charge of something, if you find it on the periodic table to be a representative or a main group element, you can probably reasonably predict its charge. For example, the group 1A, the first column on the periodic table, when they become ions, they become +1 ions. Group 2A, they become 2+ ions. The transition metals, they also form ions, they form cations, but they tend to have variable charges. We can't just find their location on the periodic table and predict what their charge is. So moving across to group 3A, aluminum, gallium, indium, they form 3+ charge. So what we have is a trend going, but we have to ignore the transition metals. As we move from left to right, we go from 1+ to 2+ to 3+. Well, that trend ends at that point, but at least it's handy for those elements. So remember that they form plus ions, cations, because they're metals, and metals lose electrons when they become ions. So now we have the nonmetals. They form anions, negative ions, by gaining electrons when they become ions. Group 8A, they're very unreactive. They don't form charges. Group 7A, fluorine, chlorine, bromine, those become -1 ions. Group 6A, -2. Group 5A, -3. So once again, we've got a trend going. As we go from right to left, we have -1, -2, -3. Very handy. This last periodic table shown on this page is one that I drew, and I'm providing some terms I want you to know. So I used the term group to describe group 1A, group 2A, and so on. Those columns can be called columns, but most commonly they're called groups or families. Families having to do with how family members often have similarities. Elements within the same family often have some chemical similarities. The group 1A metals, so again, not hydrogen, but the metals in that group, those are specifically called alkali metals. They become +1 when they become charged. Group 2A metals are called alkaline earth metals, and they become 2+ when they become charged. The transition metals, so they can have variable charges except for a few of them that I want you to know. Zinc, when it becomes charged, always it is zinc 2+. Cadmium, below it, when it becomes charged, is Cd 2+. And silver, beside the cadmium, when it becomes charged, is always +1, so Ag+. And then we have group 3A, they become positively 3 charged. And then we go to the nonmetals, and the group 8A, those are referred to as the noble gases, so that's hydrogen, helium, argon, etc. The group beside that, group 7A, fluorine, chlorine, those are the halogens. They become -1. Group 6A, -2, group 5A, -3. And we have, of course, the reminder, the metalloids are the ones that are on that staircase, the separators between the metals and the nonmetals. Then we have the lanthanides, the actinides down at the bottom. Alrighty, so our next section is on nomenclature. That's how we name compounds. So going to the bottom of this page, to name a compound, we must first decide from its chemical formula whether it is a molecule or a salt or an acid. So we're going to go through how to name molecules, how to name salts, how to name acids. But we have to know what kind of a compound it is, because molecules are named one way, one set of rules, salts another way, another set of rules, and then acids have their own way to be named. So molecules contain nonmetal elements. Salts contain cations and anions. They contain ions. And acids contain nonmetals, usually nonmetals. Often hydrogen is written first. So the common acids, the acids we will deal with in Chem 1, contain hydrogen, and it's often written first. Alrighty, so going back up here a little bit more. Molecules contain nonmetals. H2O, that's, of course, you know, water, that's a bunch of nonmetals. That's a molecule. And we have the atoms covalently bonded together. That is to say, they share electrons, and that's what's holding the hydrogen and the oxygen together to the molecule. We see that H2O is the molecular formula. When we're showing how the bonding is occurring, that's called the structural formula. Covalently bonded compounds are called molecular compounds or simply molecules. Salts, those are composed of ions that are attracted to each other because of their opposite charge, where an ion is an atom or a group of atoms that has a net positive or negative charge. CuCl2 contains Cu2 plus and Cl minus. So that is a salt. Copper becomes Cu2 plus by losing 2 electrons. So Cu yields Cu2 plus 2 electrons. The electrons are separated, so we're left with a cation, Cu2 plus. Cl forms Cl minus by gaining an electron. So one of those electrons from copper goes to Cl to make Cl minus. A reminder, a positively charged ion is called a cation, and a negatively charged ion is called an anion. The force of attraction between the cations and the anions is called the ionic bond, and it's just the opposite charges being attracted to one another. Ionically bonded compounds are called ionic compounds or simply salts. So we had said above that ions can be a charged atom or a charged group of atoms. When they are a group of atoms with a charge, they are called polyatomic ions, many atom ions. NH4 plus, NO3 minus, those are polyatomic ions. Ionic compounds are neutral overall. For example, if we have an ionic compound that's composed of Ca2 plus and F minus, when we put them together and write it as a neutral compound, we have to have 2 F's for every one Ca2 plus. So we write that as CaF2. If we have Li plus and O2 minus, we need 2 Li pluses to balance the one O2 minus. So we would write that compound as Li2O. Mg2 plus and CO3 2 minus. So the CO3 2 minus is a polyatomic anion. Those two would be on a 1-to-1 ratio with each other because of their opposite and equal charges. So it would be MgCO3. Copper 2 plus with the polyatomic anion C2H3O2 minus. Well, we need 2 of those anions, so it would be Cu parentheses C2H3O2 parenthesis 2. to make it neutral. Notice we put the parentheses around the polyatomic ion when we have more than one of them. Okay, so now we will get into how to name them. If it's a molecule, here's how we do that. Remember, molecules are nonmetals. So we name it by giving a prefix in front of the name of the first element, space, a prefix in front of the base name of the second element, followed by IDE, IDE. The prefix gives the number indicated of that element. So it would indicate how many of that element there are. Instead of using English for the number, like 1, 2, 3, we use the Greek names where 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Some of these I know you know. You've heard of a tricycle, a three-wheeled bike, so tri. Pentagon, 5-sided shape. Hexagon, 6-sided shape. Octagon, 8-sided shape. A stop sign is an octagon. A decade is 10 years, so deca for 10. If the prefix of the first element is mono, it is dropped. For example, CO, that would be a molecule. It's composed of nonmetals. That is carbon monoxide. So the mono in front of carbon, we don't say. So we simply give the name of the first element, carbon. And then we have one of the second element, so we would have mono. And then we have the base of oxygen, which is ox, and then we end at IDE. For ease of pronunciation, we drop an O, so it's simply carbon monoxide. Okay, so here are some examples for you to work with. Be sure to check your answers, so come back and do that later. All right, if it's an ionic compound, if it's a salt, we name it by naming the cation, space, anion. Cations, if they are main group metals, representative metals, that is from group 1A, 2A, 3A, then we simply give the element's name, lithium, barium, aluminum. Except for a tin and lead. Tin 2+, we write tin, and then in parentheses, in Roman numerals, we put a 2 to indicate the charge of the tin, because tin readily comes as 2+ or 4+. If we're talking about tin 4+, we have tin, and then in Roman numerals 4. So that would be part of the name of the cation. The same deal for lead. Pb2+ is lead 2+, Pb4+ is lead 4. Notice I made a typo on that second Pb. If they are transition metals, then we give the element's name, and then like we did with tin and lead, we have within parentheses and in Roman numerals the charge. Well, remember the transition metals, except for zinc, cadmium, and silver, can have a number of different charges. That is, copper readily comes as copper 2+ or copper 1+. If we're talking Cu2+, we would write Cu2. Iron 3+, we would write iron 3. Okay, so since zinc, cadmium, and silver always have the set charges, which you just have to remember, when we have zinc 2+, we just write zinc. Cadmium 2+, cadmium. Silver plus silver. Polyatomic cations. So we have 2 of them that I'll want you to remember. The 2 are NH4 plus, which is ammonium, and Hg2, 2 plus, is mercury 1. It's kind of a strange dimer, so di meaning two of these mercuries that hang out together, where each one has a +1 charge, which is why we write mercury 1. The anion, how we name that, if they are simple anions, that is just composed of one element, we give the element's root name or base name, and then we follow it with IDE. So Cl minus is chlor for the root or the base, and then ide, chloride. O2 minus, oxide. S2 minus, sulfide. N3 minus, nitride. There are a number of polyatomic anions that you will just need to memorize. And they are given in Table 2.5 from your textbook, which is on the next page of these notes. I list a few of the more common polyatomic ions. C2H3O2 minus is acetate, CO32 minus carbonate, OH minus hydroxide, NO3 minus nitrate, PO43 minus phosphate, SO42 minus sulfate. So here's Table 2.3 from your book. Names of some simple kind of ions. Table 2.4, common cations where they can have variable charges, so we have to indicate with the Roman numerals what the charge is. Here's that Table 2.5, the polyatomic anions and cations. So you'll want to be able to refer to that table and remember the names and the charges. So then we put all that together, we name the cation, and then we name the anion. If we were given the compound NH4Cl and we were asked to name it, we would have to recognize NH4 plus, that's ammonium, Cl minus, chloride. So we have ammonium chloride. CaC2H3O2, 2. We start with calcium, and then we recognize that the polyatomic anion is acetate. Notice that they are on this 1:2 ratio because we have calcium 2 plus. We know that because of its position on the periodic table. And acetate is C2H3O2 minus. Mg3N2. So we have magnesium, which is Mg2 plus. We have nitrogen, which is N3 minus. The 3:2 ratio is just to get their charges right, to have a balanced overall compound. So that's composed of magnesium and nitride. So we have magnesium nitride. Next we have lithium carbonate, ammonium fluoride. Now we have FeBr2. So we have a transition metal that isn't zinc, cadmium, or silver, so we're going to have to indicate its charge. We have FeBr2. To figure out the charge of the ion, we look at the charge of bromine, which would be Br minus by virtue of its position on the periodic table. There's 2 of those. So we have overall for the 2 Brs, we have -2. We have 1 iron to balance that, so iron must have a 2 plus charge, and that's how we know to write iron 2 bromide. Same thing we apply to the copper compound below. So Cu2O, O is O2 minus. So the copper, there's 2 of them, has to share that 2 plus charge, so each one is Cu plus. So we have copper 1 oxide. Silver iodide, it's a transition metal, but it's silver, so it always has a +1 charge. So here are a number of problems for a number of chemicals for you to come up with a name or the the molecular formula for. Check your answers. Acids. So, when dissolved in water, acids produce H+. They are corrosive. If you spill some acid on your hand in the chem lab, you'll feel a little bit of an itchy sensation, and you can just wash it off with water. But that's due to the H+ that they produce. So acids contain hydrogen. It's usually written first. We have acids that contain oxygen. We have acids that do not contain oxygen. And here are the acids that I want you to recognize and be able to name. If they do not contain oxygen, then in the name we have hydro. And then we name whatever element is in addition there. HF. We have hydro because it's got no oxygen. And then we give the base name for fluorine, fluor. And then we follow that with ic acid. So HF is hydrofluoric. HCl, hydrochloric. HBr, hydrobromic. HI, hydroiodic. CN is cyanide, CN minus. So we take that, the base part, cyan, and we have in the front hydrocyanic acid. H2S is hydrosulfuric acid. Acids that contain oxygen, like HNO3, so to name those, we use the base name of the element other than hydrogen and oxygen, and then we either follow it with ic acid or us, OUS acid. The ic acid is the one that has one more or more oxygen. So if we compare HNO3 and HNO2, they're both going to start nit with the R, nitre, and then the one with more O, ic acid, the one with less, us acid. So HNO3, nitric acid, HNO2, nitrous acid. Then we get to H2SO4 and H2SO3, sulfuric, more oxygen, less sulfurous. H3PO4, phosphoric acid. HC2H3O2 is acetic acid. That's coming from acetate. C2H3O2 minus. Alrighty, so here's another little summary of that. Here's an example, a big table for you to fill in. So it's asking you to fill in the missing formula, the type of the compound, and or the name of the compound. So I either give you the chemical formula and the name and you provide the other one. You also provide the type of compound. So N2O4, that's composed of nonmetals, so its type of compound, it would be a molecule, and you would name it as you would name a molecule. Remember, molecules have those prefixes like di and tri and mono and so on. So this compound would be dinitrogen tetraoxide. Next we have aluminum phosphate. Okay, so that's composed of a metal, which becomes a cation. So we're talking, and of course an anion, the phosphate. So we're talking about a salt or an ionic compound would be the type of compound. And then we would give the chemical formula. Aluminum is Al3+. Phosphate, we have to know from the polyatomic anion list, it is PO4 3-. So we make it neutral. We need one of each because of their opposite but equal charges. So we have AlPO4. Alrighty, so do go through all the rest of these here, and we have some of them as acids in here, and then next we have the answers. So that's the end of our chapter 2 notes. So be sure to go over this video again, as that helps you go through the handout. Make sure you've done all the examples. Read the chapter 2 chapter in your textbook and do the assigned homework problems.